speaker will be Krall from Thornton Tomasetti, I think in the New York office? In the New York office, and he's got another fascinating building for us to have a look at. Callow?
Oddly enough, this is the third time that I've presented the New York Times after Ahmad or after the Hearst building has been presented. The buildings are spectacular. Both of them are, it's basically bringing European architecture to New York City, and they're both wonderful changes to the skyline. The New York Times, go ahead, and actually, I'm going to run through these slides rather quickly. At the end, I'd like to get into some of the sustainability issues and some of the things that the New York Times did to make this building a little more sustainable. And as Bart had mentioned, this is mainly a structural presentation, but if you can, well, I know where Gary Pomerantz is. He went to South Africa, and he also was a mechanical engineer on this job, and he could give you some insight into some of the other systems. The structural challenges. The New York Times moved into Times Square and hence lent the name to Times Square in 1904, and they occupied their building for 100 years. And the design challenge brought to the design team by the New York Times owners basically was to design a building that would last for the next 100 years. The New York Times partnered with 4C Ratner, a local developer, and they were great partners. They were very different people. New York Times were incredibly inquisitive and would experiment with anything that the design team came up with, be it terracotta or ceramic on the outside of the building, underfloor air systems, or carbon fiber. They would set up summits. They would bring experts in to talk to us and experiment with all these type of systems. And 4C Ratner, they pulled back on the reins whenever we got a little too close to our budget. So they played the good owner, bad owner role very, very well. The building was a design competition, and in 2000 awarded to Renzo Piano. Renzo partnered with FX Fowl, who have offices in New York City and also in Dubai. The primary design feature of this building is its transparency. The facade, the skin of this building is ultra clear glass, and it's shaded by an exterior curtain wall shading system of ceramic rods, closely spaced ceramic rods. You can see on the lower side here, this is a shot of the podium, and the podium is where the newsroom is. It's a 5-story structure, and Renzo's vision was to bring the newspaper and the newsroom to the streets and to the people, and the transparency. Basically, you can stand outside and watch all the activity going on inside the building. It's so transparent that you actually see the structure not only inside the building, it's exposed and outside of the building, and we'll get into that. This is a picture of the site on 8th Avenue. The tower was oriented up against 8th Avenue and located between 40th and 41st Streets. A picture, an elevation of the building, a 52-story, very slender building of almost 750 feet with a 300-foot tall mast on the top of the building. I've got some pictures of the mast at the end. The podium is where the newsroom is. The New York Times basically occupies all of the podium structure plus halfway up the building to the outrigger zone. 4C Ratner leased out the space on the second half of the building, and they've said it's one of the most successful projects they've ever worked on. There is opportunities for the New York Times to move up into the building as time goes on. This is a picture, just a quick picture of the floor plate, and we have a 40-foot lease span to the exterior columns, but there's a 5-foot cantilever beyond the columns, so it's 45 feet from core to facade. And these corners, this mouse doesn't want to work, but you can see the 4 corner notches, and originally the design competition had exterior stairs in those corner notches in a glass facade, and that was Renzo's. Renzo called it his sort of the fire escapes of Hell's Kitchen, because this area is very close to an area in New York called Hell's Kitchen. They got value engineered out of the project, unfortunately, but the notches remain. The challenge was to come up with an efficient lateral load resisting system, and you can see in the east-west direction there are 3 lines in the core of the building, and there are 3 lines in the north-south direction. Unfortunately, on grid 5, we couldn't get a brace frame in there because of the service cars, so we were lacking a little bit of resistance in that direction. The dotted lines are outriggers, and outriggers at the 28th floor and 50th floor reach out and grab the perimeter columns and basically use them as crutches to increase the overturning resistance of the building. We optimized the building for strength under gravity and lateral loads, but even though we met strength requirements, actually in this slide you'll see it says that we've got large deflections and we didn't meet our occupant comfort as far as accelerations are concerned. So the answer to that is either to throw more steel into the building and make it a stiffer building, or I was mentioning that Renzo lost the stairs on these notches, and this was an opportunity to put something back into those notches. And with our PVW, we worked out this exterior bracing system that would add to the stiffness of the building. And the unique thing about that is that we always ran 2 scenarios for this building, one in which the core alone was resisting loads, and one that had the core and the exterior bracing. The core alone is sufficient for strength in the building, but when you put the exterior bracing in, we meet all of the deflection criteria plus our acceleration criteria, and that means we didn't have to fireproof the rods. They're only there for serviceability. Here's a picture of that, of the corner, and you can see the exterior rods. Those rods were pre-tensioned. Basically, under wind load, you're going to get a compression in one series of the rods and tension in the other. We pre-tensioned these rods. The rods are manufactured by a company called Dabber in Sheffield, England. There's also Callow is their neighbor and their competitor. They both have similar systems, but they've got these hydraulic systems that will pull these 2 rods in together at the turnbuckle, and you can see in the lower. Actually, it's a little dark up there, but there's a turnbuckle, and it's a sleeve, a double-threaded sleeve, and as they pull these 2 rods together, there's a guy on there, and he just keeps turning that the sleeve until he gets to the point where we've got enough stress in those rods, and then they just let go and it binds. They said that they could come up with a tension, or they were accurate within 2%. Here's a picture of the installation of the rods, and you can see we have double rods, and they cross each other, two in a vertical orientation and 2 in a horizontal, and they just cross each other in the middle. Exposed structure was another challenge here, and right there that arrow is pointing to an interior beam that's coming out and grabbing. Because we have 8 columns outside of the building, the interior structure has to come out at 16 locations and grab this exterior column. It presents all kinds of challenges. Basically, it is coming in under the floor slab. The New York Times wanted to raise floor system, so the interior beams are traveling below the slab, and if they would keep going straight into the column, they would be eccentric to the spandrel panel. In fact, they'd be so low they would actually hit the glazing of the facade. So each of these beams does a dog leg before it gets out and attaches to the exterior column. So detailing the exposed steel was obviously critical. This is part of the architecture, and you can see it is. It really speaks on this building. We've got exterior columns, we have exterior beams, and these exterior rod systems. We detailed these work hand in hand. Actually, as Bart had shown, you had a balsa wood model. Renzo, they created hundreds of these models, trying to figure out what the orientation of the rods would be, and we finally came to a conclusion that we could make this work, and then we detailed it highly detailed. It gave all the radiuses, gave all the plate thicknesses, weld sizes, and everything, because this was part of the architecture. We also, New York Times was great because they would do a mock-up of everything, and this is a 6-ton piece of the knuckle that we call it the knuckle, where the horizontal beam, the rods, and the column all come together. And you can see there's some post-it notes on there because after this was built and it was sitting in the old loading dock in the New York Times, they brought all the fabricators who were going to bid on this job, and so they could come and touch and feel this, and they would put post-it notes on and say, well, we don't like that, and this has got to look a little bit better. And all the fabricators kind of chuckled at the terrible look of the splice. That's the bad line on the column. And you know, these guys all bid. They knew the fabricator who actually put this together, and they couldn't believe that they screwed it up that badly. But we actually told them that we didn't want it to be perfect because we wanted to see how bad it would be if it was off by 5/8 of an inch one way or the other. And that was unacceptable, and we knew that. And so the solution was Serge here, who's from Renzo Piano's office, is there watching the fabricator measure the offsets, and Serge was on site every day, and he would go out there and he would write down all kinds of notes and come back to the erector and say, you know, the northwest column is off by 1/8 of an inch this way, and it's rotated a little bit. And he made friends with all the erectors, and I thought they were going to throw this little French guy off the building, but it worked, and it's amazing how well all the tolerance was, and these guys went out there and corrected all of his problems. You'll see Serge a little bit later. One of the other issues with steel being outside the building is that it's obviously exposed to a different temperature than the interior of the building. And because of that, we ran lots of models with different temperature ranges, and the outside columns, which are shown in blue, are going to shrink and grow with temperature changes. The inside columns, which are always at an interior temperature, are going to remain the same. That last bay is 30 feet, and that last bay could see a 3-inch difference between interior column and exterior column, and 3 inches over 30 feet is unacceptable. The solution was to add some trusses. We already had outrigger trusses at the 28th floor, and we had some outrigger trusses on the 51st floor, but adding another thermal truss at the 51st floor helped even out those changes, and basically the interior column gets pulled down and pushed up with the changes with the exterior, plus the truss restrains the exterior column. And we were able to limit those changes to LN300, which was acceptable. The other benefit is that all these trusses, these belt trusses and outrigger trusses, add a lot of redundancy to the building. The cantilever bay system, in between the two notches on the north and south, the areas in orange, don't really have any columns that come to the ground. The vision was so that this would be floating above the storefront, and you can see in this picture there's no column in that zone above the storefront or at the storefront. The way we solved that was to add on these two lines here and here, add some rod bracing that would be outside the building and hold the floor up and satisfy facade deflections. The center bay, we couldn't put a rod in there because it would be going through someone's office space, so we created a Varendeel system. There you can see the exterior rods. Inside that system, we created a Varendeel moment frame, and we had to run that system through multiple series of construction sequences. So as you slowly, as this Varendeel grows taller and taller, the amount of deflections that keep adding up become less and less. So, or the increment becomes less and less. So at some point, when we reach the outrigger zone, we get a brace at the 28th floor. But at that point, we've already accumulated maybe 3/8 to 3/4 of an inch of deflection at the base, and so we had to camber all this up. There was a temporary diagonal at the base that was installed and then removed later. The mast is the final, the capping, the cap to this building. It's a 300-foot tall mast. It is cantilevered off of the top of the building. Basically, it extends one floor into the building, which is a double height story, and the wind load on the mast is resisted by shear in the 2 floor slabs. The mast at the base is 8 feet in diameter, and it's big enough to get some of the design team inside. And at the tip, it's 8 inches. Now these pictures, actually one of these pictures, the next picture is on Renzo Piano's website, but the other two may not have been seen before. Oh, sorry, that's coming next. The mast erection, it was put up in 3 pieces and it was all bolted. But here are pictures of Serge and Bernard Plattner climbing to the tip of the mast. And they're almost 1,100 feet off the ground. One of the things, if I have time, I want to get into the exterior facade and talk a little bit about what Glenn Hughes at the New York Times had done. You see the picture in the top is the facade system. It's clear glass, but it's got this facade of ceramic rods out in front that act as a Venetian blind to block sun from entering the building, except for the vision zones. When they heard about how clear glass was going to be used in this building, they were excited and they realized they could get some savings in daylighting because of the clear glass. David Thurman and Glenn Hughes contacted Lawrence Berkeley Labs, LBL, and said, hey, we want to do some systems that take advantage of our daylighting, mainly dimming systems so they can turn some of these lights off and allow daylighting to be used on a regular basis. But and only 2% of office buildings in the U.S. use dimming systems. LBL actually turned to them and said, you've got a bigger problem than that. You're going to have too much light coming into your building. You're going to have glare issues, and especially in the low angles of sun, you're going to have sun entering this building all the time. So the solution was, in the bottom picture, was to build 1/4 of the floor plate on their parking lot at the printing plant in Long Island. And they mocked up exactly 1/4 of their floor plate. They put the exact curtain wall on with the exact rod spacings. They put all the furniture that they had already designed into the building. They put computer monitors in there with video cameras, and all of this information. They had monitors that knew how much light was in the building, how much heat was being absorbed into the building, and that was all being sent out to Berkeley, where it was being analyzed. At the same time, they got shade manufacturers from Mecco Shade and Levelor to come in and set up their systems and automate those systems with the amount of sunlight that's coming into the building. They also knew that obviously the path of the sun was going to affect this, so they had computers that understand where the sun's going to be at what time of the day, and they also have a radiometer at the top of the building that would determine if it's a sunny or a cloudy day. So all these systems communicate with each other and raise and lower the sun shading systems automatically, and then dim or turn off lights whenever it's deemed that they've got enough light inside the building. It was an incredibly successful mock-up, and it just goes to show how inquisitive the New York Times ownership was to go out and spend this kind of money to do this study. Lawrence Berkeley Labs got a grant from the U.S. government to do this study also, and they're using that information now for future buildings. David Thurman's an incredible guy at the New York Times, and he said that the best part about innovation is sharing that information. And I can get you in touch with David or Glenn if you're interested in these type of shading systems. It really, the other day, Glenn called me up and told me that he was looking out and half the lights on his floor were off. And I was looking out at my office and they were all on. So it's really working. That's it.